everyone, and thanks for that, Michael. Much appreciated. Forgot that you're giving us instructions in the chat. So it's a pleasure to be hosting this session. My name is Russell Brewer. I'm based at the University of Adelaide, and I am pleased to present my colleagues who have also joined from San Jose State University, that being Associate Professor Bryce Westlake, Enrique Guerrera, and Francesca Fanucci. Today, we are going to run a session entitled Using Automated Methods to Detect, Analyze, and Investigate Cybercrime. We've got a total of 3 papers that we're going to present today. What we might do is we'll present one paper, have a question period. If anybody has any questions as we're going, we invite you to write those questions into the chat. And then we might answer the questions from that session, then move on to the second paper, questions, then move on to the third paper. So we'll start today with a paper that will be presented by Bryce Westlake and myself. Our paper, let me just pull it up, is entitled Developing Automated Methods to Detect, Match, and Analyze Child Sexual Abuse Videos Using Face and Voice Biometrics. So today we're going to do just that and talk about just that, share with you an automated platform that we have developed that has been designed to detect, match, and analyze new child sexual abuse videos using face and voice biometrics as they become available online. So today's presentation with Bryce and myself, we'll be delivering on behalf of a much larger team of computer scientists, criminologists, psychologists based at San Jose State University, Simon Fraser University, Michigan State University, the Defense Science and Technology Group here in Australia, as well as Flinders University. So today's presentation is going to be broken into 3 parts. First part, we're going to provide you with some background, outlining some of the problems that are currently facing investigators with respect to the detection and investigation of child sexual abuse material on the internet, and provide a rationale for the development of this software platform and its intended capabilities. Next, we're going to shoot into a demonstration of this tool and its current capabilities. And in doing so, we'll also talk through some of the results of our performance testing. We'll finish up with a brief discussion of the implications of this work and some of the directions for future research that we plan to delve into. So without further ado, I'm going to hand over to Bryce Westlake, who's going to talk us through some of the background and rationale. Take it away, Bryce.
Excellent. Thanks, everyone, for joining us today. So we're really excited to present some of this information and talk to you about where we're going to be going with it as we see it being applied, obviously, to child sexual abuse media, but also to a lot of other domains. And I'm sure as we go through this, you'll see some of those different areas that it could be used. So we'll move to the next slide there. So it's increasingly—
just so everybody's aware, you might want to put this on. And in fact, if Michael and Raphael are watching, if you could make my screen the principal screen, that would be great, so we can follow along.
Yeah, so it's increasingly being recommended that the combating of child sexual abuse material distribution online rely more on automated detection techniques. And this is because of the continually increase in abundance of media being distributed and the psychological and physical harms examining these cases has on investigators. So currently, most automated techniques rely on hash values for identification. Hash values act as pseudo-digital fingerprints for computer files, with any alterations made to the file resulting in a new hash value. So more specifically, if an offender edits an image or a website resizes an image upon uploading, a new hash value is created. And so the use of hash value databases to combat child sexual abuse media distribution can be effective, but it does have 4 limitations. So first, the precision of hash values is also their biggest limitation. An analysis of more than 23 million reports to the National Center for Missing and Exploited Children found that 91% of videos were only flagged once. Put another way, child sexual abuse media is constantly modified, meaning that requiring the exact same file to be present on multiple websites is not very effective. Now, this has been addressed to some degree through tools such as photo DNA, which allows for slight alterations, increasing the number of similar images that are identified. However, fuzzy hash algorithms like photo DNA cannot account for large alterations, such as changing the background or adding an additional person or items, nor recognize links across media files. And we'll talk about the importance of this shortly. So second, the majority of hash value databases have been developed around images. Unfortunately, recent reports demonstrate an increasing preference among producers and consumers of child sexual abuse media for video files and lucrative on-demand live streams. In fact, 2019 marked the first time that reports of child sexual abuse media had videos outpacing images. As videos become more prevalent, reliance on image-based databases will lead to a law of diminishing return due to their continued reduction in prevalence. And this is especially new when we're talking about new child sexual abuse media. So third, for a hash value to be present within a database, it needs to be previously known. This effectively removes the ability to detect new media as it enters the online marketplace. This has been noted by integrated child exploitation investigators as one of the biggest challenges and can delay or prevent the ability to ascertain an individual's identity or a victim's location for rescuing purposes. So the necessity for substantial human intervention for verifying the media and incorporating it into a database is also a problem. These investigators experience high burnout rates due to unmanageable workloads and insufficient time and resources. In addition, they experience significant psychological harms, suffering from secondary traumatic stress disorder, emotional exhaustion, intrusive thoughts, and interpersonal and marital problems. The continually increasing amount of media being reported and needing to be reviewed, coupled with more video production, which is likely to be more traumatic than images due to the moving visual and auditory accompaniment, suggests that the negative impacts to investigators is likely to increase significantly over the coming years. Fourth, the identification of child sexual abuse media through hash values simply states that a known piece of media has been detected. Without significant manual involvement, it's impossible to link one image or video to another. Like with detecting new media, being able to link media can have important implications for apprehension of offenders and rescuing of victims. This is because small pieces of information from multiple images or videos can be combined to identify locations, people, and other important information. Furthermore, being able to make this link without an investigator having to manually review the media, exposing them to graphic content, makes linking child sexual abuse media even more critical. So because of these limitations, the use of biometric attributes found in child sexual abuse media is the next phase of combating distribution. And this has already begun with the introduction of facial recognition, but has the potential for so much more. So what's the solution? Well, the limitations of hash values point to other attributes being the better path forward for detecting child sexual abuse media online. One potential avenue is the use of biometric attributes for identification. And so soft biometrics include physical and behavioral characteristics, such as skin, eye, and hair color, as well as gait, so a person's walk, and tattoos. While hard biometrics include physiological characteristics, such as face, iris, and voice recognition, fingerprints, and palm veins. As one of the most researched and developed biometric attributes, facial recognition seems the most likely to replace or at least supplement hash values. Thus far, this work has focused on distinguishing between children and adults, pornographic images from inoffensive images displaying a lot of nudity, skin tone and skin color, and non-facial skin marks such as vein patterns. So these studies, along with others, have identified several problems in developing these tools. These include the challenges of estimating age, the lack of distinct facial features in children, backgrounds clashing with the skin tone of the child, and child sexual abuse media without faces, and the ethics of using biometric data in general. So despite the advantages and advances of facial recognition, it's important that multiple biometric attributes are used for identifying victims and offenders. This is because some of the problems identified with facial recognition can never truly be eliminated. As a result, grouping of similar content such as faces with voices, may be required. And this can extend to include attributes such as skin tone, sex, gender, age, vascular patterns, and non-visual biometrics, such as language spoken and tone of speech.
On to me now, Bryce.
Yeah.
Yeah, great. So now I want to talk about the importance of triangulation, because ultimately what these tools can provide, or what this tool can provide, is a capability of using multiple biometric cues to triangulate matches. That is, matches between victims and matches between offenders across what could be very large or small data sets. Now, this can actually reveal some really, really important patterns of offending, including patterns of co-offending, but also patterns of victimization or co-victimization across broader networks. So here in this slide right here is just an example of what this could look like. So here in this very small example, and you could imagine this example expanded out across thousands, hundreds of thousands, millions of videos, but we've got 4 videos here. We have 3 offenders, 0, 1, 2, and 3, and we've got 4 victims, V, 1, 2, and 3. And we can see the lines, the green lines indicate a face match, so face recognition, and the red lines denote a voice match or speaker recognition. And we can see here in this example that all of the offenders are actually linked together through co-victimization of the same children. They're not appearing in the same videos, but we can see that there are links that can be drawn between each of them by leveraging 2 different types of matches. Offender 1 and offender 2 are actually linked via both victimizing victim number 1, and offender 2 and 3 are linked through their shared victimization of victim number 3. And also the inverse is true, that these victims are also all linked together through victimization, through particular offenders. So importantly, what's important to see in this example is that these links would not be possible to be established had it not been for the combined and triangulation of different biometric cues. With face alone, we would lose victim 1, victim 2, and victim 3 completely. So bringing these together and looking at patterns that might exist across a broader data set can be particularly useful. So designing a tool that can integrate multiple biometric cues is of, and we argue is of, immense importance. So what I'm going to do now is speak to the provide a demonstration of our tool in action. Now, our software platform actually comprises 2 separate tools. The first, a web crawler, which can crawl the internet and detect new child sexual abuse material as it becomes available online. And the second, our Biometric Analyzer and matching software. So I'll start by providing a brief demo of our web crawler, known as the Location Extraction of Child Exploitation Networks, or LECENE.
LECENE is a custom-designed web crawler initially developed to scan surface web websites distributing child sexual abuse media and identifying known image hash values. LECENE has since been updated to function on the deep web and extract additional information. We start the data collection process by identifying website URLs where we want LECENE to begin. We can then restrict the data collection process to these specific websites or continued websites hyperlinked to the starting website. We can also place a cap on the size of the web crawl based on the number of websites or the number of web pages. Finally, we can identify domains that we want to exclude from the web crawl. We can then require specific criteria to be present for the data to be collected, such as a minimum number of self-selected keywords and/or a minimum number of hash values. We can also set LECENE to download attached videos and/or images. Once we've determined our criteria,
The scene begins the data collection process. Any images or videos that have a corresponding URL, such as attachments, can be downloaded and stored in a separate folder. The textual information associated with the name and location of the media is stored in a separate database.
Whoops. Now, moving on to the second component, once those videos have been identified, download and saved to a local directory, we can ingest those videos or media into the Biometric Analyzer and Network Extractor tool. This is a demonstration of the Biometric Analyzer and Network Extractor. Once the videos are downloaded by the web crawler to a local or network directory, they can be imported or ingested into the Biometric Analyzer and Network Extractor. This is done first by running a single command that will engage a 5-step process. In this example, we are ingesting 40 videos of celebrities and politicians downloaded from the internet, constituting 8 different subjects with 5 videos each. At step 2, the videos will be processed. That is, the tool will sample each video and extract any faces that appear within each frame. Here, a high-quality reference face for each subject will be selected in order to increase the matching performance at future steps. At this step, the audio will also be separately analyzed and voice features extracted. At step 3, the videos will be matched according to the face and audio biometric features extracted. At step 4, the performance results are reported in the form of various ROC curves and histograms, including for face matching, for voice matching, and for fusion. The matching methodology can also be adjusted here according to user specifications. At step 5, users can further explore match results using a custom GUI that we have developed for this purpose. The GUI can be accessed using our integrated local web server and any web browser. I will now take you through some of the features of the GUI. First, we can jump over to the face viewer where we can see each and every face that has been extracted from every frame within the video. So we'll head over to our example here, Julia Gillard video number 3, and we can see a range of different faces have been extracted. When it comes to audio, for this particular demonstration, we have extracted the audio as a single clip. So here again, we can see if we go to Julia 3, press go, you can see that this is the audio, 1 minute of audio that's being extracted. We can play that directly within the GUI.
That policies and plans are at the centre of our national discourse.
Now we can go over to our audio match viewer, where we can see on the left-hand side, we have video 1 matching over here with video 2, and you can see that there's a match score associated with that particular match. So if I go over to our Julia 3 example, and what I'll do here, rather than I can show matches from one video to the next, but what I can also do is show the matches from the audio matches from Julia 3 to all videos within the database. So by just clicking all and then pressing go, and then we can see here that the clip has matched Julia 4 with Julia 3, and we can play that.
That lyrical, that mythical, that political. Tim Winton's Clouds.
Video 1 and then video 2.
That policies and plans are at the centre of our national.
So we can see it's correctly identified a genuine match between Julia video 4 and Julia video number 3. We can do the same over here with the face matcher. Again, I will go down to our example of Julia 3, and in this instance, I'll go down to all. I'll press go, and we can see all of the different matches between video 1 and video 2 for this particular subject, with our match scores listed here on the right-hand side. This is beautiful. So now what I'll do after that demonstration is turn to a discussion of the performance results. Now, today I will detail the results of actually 2 different performance tests. One, I will actually provide some information about the performance of the tool operating on the data set that is outlined in that video, in the demonstration video. So of 40 subjects of politicians and various internet celebrities. And then second, I'll provide a performance test data for a separate data set of 100 videos of adult pornography. And we'll talk through some of the differences and some of the challenges of using this tool in a pornographic setting. So what we're looking at here are the results for both in fact, I'll make it bigger so you can actually see it. But we're looking at the results for both the face matching and the voice matching distinctly. So when we're looking at these, we call these rock curves for those who are unfamiliar, and we're seeing the true match rate here on the y-axis being mapped against the false match rate here on the x-axis. And this is mapped at a match score cutoff of 0.6 for face and 0.8 for audio. And what we're seeing here when we're talking about this non-pornographic performance test is that with face, we're seeing near flawless performance, that we're getting at a true match rate of 100%. That means the tool is correctly identifying all of the correct matches. We are seeing a false match rate of about 7%. So in order to get 100% of all of the genuine matches, we see about 7% of false matches or false positives are being identified alongside. If we only get 95% of the true matches, we get a false match rate of only 1%. So very good performance. As expected, when we look over at the audio, because audio or speaker recognition is not as developed as expected, we saw values that were lower than what we saw for face. So at about 50% here, of getting 50% of all true matches, we're getting at only about 5% false match rate. When we get up to 75% true matches, we're getting about 25% false match rate, and so on and so forth. Critically, when it comes to this rock curve, we're seeing the true match rate is outstripping the false match rate as is being presented. So again, we're actually very happy with this performance based on videos that were collected from the wild, not trained in a laboratory setting. Moving on to our second test. This is a database of 100 videos, 36 subjects, collected from the internet, adult pornography actors, 2 to 3 videos each. We see differing results. We see slightly lower results for both face and for voice. Now, critically, we were actually incredibly excited about these results because pornography represents a very, very, very different context than the type of data, the types of videos, the types of image, the types of audio that these algorithms have been originally trained on, right? So we see in pornography, and I'll encourage you to use your imagination. I'm not going to provide any examples here, but humans are oriented in very, very different ways than we might expect. They might be wearing costumes, they might be wearing tons of makeup, their hair be done extravagantly. We might see unexpected body parts appear in frames alongside faces. And also the voiced audio is very, very different. Gone are the monotone, straightforward conversations. And instead we get a lot of moaning, screaming, shouting, sexy whisper voices, and a wide range of other interesting sounds that might come out of those videos. So this produced significant challenges and particular and context-specific adjustments to the tool to be able to accurately extract reference frames and audio that could be matched across the data set. So when we look at that performance result, we still see quite good performance on face. We see the vast majority of genuine matches are being found at still a very, very low false match rate here. When it comes to audio, we see, again, importantly, the true match rate is outstripping the false match rate. So we're picking up more genuines at a faster rate or higher clip then we're seeing false matches being identified. So great performance still on face, performance that we were very happy with, given that this is a prototype tool with speaker recognition, showing that this tool can and does work in pornographic settings. Here we see at about 50% true match rate, we got about a 22% false match rate. So with those results in mind, I am going to turn it over to Bryce, who's going to talk you through how these results can be interpreted and what the implications of these results might be.
Excellent, thank you. So while the ROT curves are useful for visualizing all possible outcomes, we feel it's beneficial to also look at some specific numbers. So using the default face and voice match thresholds for face, that's a threshold of 0.60 and below, and for voice, that's a match of 0.8 or above. The genuine or true and imposter or false matches are displayed here. And so using facial recognition alone, 88 of 92 genuine matches were identified. While 4 genuine matches were not identified with facial recognition, 3 of those 4 were identified with with voice recognition rather. In other words, 91 of 92 or 99% of genuine matches were identified by either facial or voice recognition. And equally as important, 63 or 69% had both a face and voice match. And so these findings point to the importance of using multiple biometric markers instead of relying on one, even if one, such as face, is fairly accurate. So while 225 imposter pairs had both a face and a voice match, this accounted for only 4.6% of the data. As expected, there were fewer imposter pairings with face alone compared to voice. Most importantly, 2,353 or 48.4% of the imposter pairings did not match on either a face or a voice. And so looking at this from an investigatory perspective, using face and voice, we can be confident that we will identify almost all child sexual abuse media. While we will encounter false matches, we can also cut an investigator's workload in half by simply excluding all pairs without a match, as only one of our genuine matches was not detected. So as we can see here, if we improve the voice detection component, which we have suggestions as to how best to accomplish that, our model will be significantly better. Next slide. So what does this all mean? So the aim of this research was to begin addressing the limitations of hash values by developing alternative techniques. We did this by developing a prototype software infrastructure that can autonomously scan the surface and deep web and collect potential child sexual abuse videos, then analyze and match the videos using facial and voice recognition. Results support facial recognition as a potential alternative to hash values for identifying child sexual abuse media. It has advantages over hash values in that it's less restrictive to media changes, such as cropping, resizing, inverting colors, and so forth. Also, it can be applied to both images and videos and can link pieces of media as being of the same person. If a database of known victims or offenders exists, facial recognition can also be used to identify new child sexual abuse media through linking newly analyzed media to existing media. The introduction of facial and voice recognition into automated tools for identifying child sexual abuse media shows promise. It effectively addresses some of the biggest frustrations of investigators by providing the possibility to A, identify new child sexual abuse media, and B, match the media. This can also be effective if investigators are given a non-child sexual abuse media image or video of a child to determine if anything, any child sexual abuse media being circulated is of the child. With the growing amount of media needing to be analyzed by investigators, biometric attributes may serve as a potential data reduction technique with minimal concern about lost genuine matches. Moreover, minimizing exposure to the media or other types of content by narrowing down the material investigators need to process may be integral, given that investigators are now routinely overworked and burnt out. In addition, by having to review entire media databases and narrowing the analysis down to just a face or voice, there's an opportunity to reduce exposure to graphic content and the negative psychological harms that can come. And so I'm going to pass it back to Russell here, and he's going to talk about what we're going to be doing going forward.
Great. Thanks, Bryce. So, future directions moving forward. So critically, we have designed the software infrastructure so that it can be extendable. And we've done so because we realize that there are a number of different, this tool can be augmented with a number of additional capabilities that can greatly and vastly increase its utility. So let me make that a little bit bigger for everyone. So in terms of future directions we can do, we really look at this in terms of improvement in two different areas. First, improving the detection of child sexual abuse material online. So one particular avenue that we're interested in is enhancing the video detection and extraction capabilities of the web crawler. At this point, our web crawler is designed to collect media that appears online that it comes across in the form of URLs or links. And one of the areas of increasing importance, particularly with respect to video, is that of streaming, as Bryce talked about earlier. So redesigning the web crawler so that it can identify and extract video from streams, i.e. camming or social media platforms, could be of immense utility. In addition, implementing computer vision could also be incredibly helpful. So insofar as the tool being able to establish whether or not media that it is identifying and ingesting is indeed pornography. So does this video contain children? Yes or no? Does this video contain pornography? Yes or no? If yes, ingest the video and extract the biometric characteristics. If no, disregard the video and move on to the next. Beyond improving the detection of child sexual abuse material, we're also interested in improving the subject matching and linking capabilities. And this can be done in a number of different ways. First and foremost, training. Training is of immense importance. As we discussed earlier, the algorithms that have been incorporated into this tool have been designed, developed, trained around pre-existing data sets with audio and faces that are not necessarily consistent with the context for which this particular tool is being deployed. So we think that there's going to be immense value in developing and retraining these models using a database of videos that is relevant to the specific context, pornography and children. Second, moving beyond retraining, we're also interested in incorporating additional biometric cues to permit additional triangulation. So looking at things like age, gender, hair color, eye color, vascular patterns. These are all other extant biometric cues that can be extracted and can be matched across video. It's just a matter of implementation and then retraining as necessary. Beyond that, we're also looking at different ways in which we might be able to integrate and expand upon the matching of biometric cues with natural language processing. Our web crawler can extract a series of metadata associated with media, be they forum posts, be they chat logs, and there are opportunities here to take that textual information and match the textual information from one user to the next across websites to be able to draw additional patterns or match patterns across larger data, larger swaths of data beyond simply media, but to also include text. So is the person commenting on what, or uploading a video on a child exploitation material forum the same person who might be commenting or participating in a live camming session on another website? So to be able to bring that together could be incredibly powerful. And then beyond that, and this is further down the road is to bring all of this together and move beyond simply matches, one biometric match in one video to one biometric match in another video, to start to compile all these data points and to be able to create identity profiles for each subject. So these are all the different videos that contain a face of this particular person, Bryce. Bryce Westlake, for example, these are all the voices that might be associated. These are all the reference points that have been extracted, and we start to match identity against identity as opposed to just video against video. That's farther down the road, but these are the directions in which we're interested in going and pursuing. So that's everything from us today. Thank you very much for listening. If there are any questions, then we would invite them on this particular project. And if not, we can move on to our second speaker. So any questions, just feel free to shoot them into the chat. So Michael's asked a question. Yeah, got that. We have seen countermeasures being deployed against artificial intelligence in the past, with turtles being misclassified as weapons by design. Is this technology just starting another expensive arms race between offenders and law enforcement? A good question. Bryce, do you want to have a crack at that one?
Yeah, sort of. Can you repeat it again? What's the first part? So just that
we have seen countermeasures being deployed against artificial intelligence in the past, with turtles being misclassified as weapons by design.
Yeah.
Is this technology just starting another expensive arms race between offenders and law enforcement?
Yeah, it's certainly something that can happen. However, having said that, it's really amazing, and I'm sure some of you have noticed too with other crimes, how many offenders or how many things are shared or distributed without a lot of fear of apprehension or repercussions for actions. And so we have seen over the last decade, especially, that you're starting to see people who are distributing child sexual abuse media start to implement detection avoidance techniques. But as you'll see with the next presentation by Enrique, and as I guess it's somewhat anecdotally that I can tell you of working in this area, you're going to find that a lot of times they don't go to a lot of efforts to hide it. And so my thought, and I think our aim with this, is that there's just so much out there. I think 2020, there was 69 million reports to the National Center for Missing and Exploited Children of potential child sexual abuse media being distributed on various websites. That, you know, you're not going to using our tool, using our stuff, you're not going to find that underground Wonder Club type thing that's doing all these different things. But you're going to stop a lot of the media that's being distributed, and you're going to find a lot of it because, as we know, not even just with child sexual abuse media, criminals are stupid, and they don't worry about being caught. And so that's usually the reason why they get caught. And so we still think that this has a lot of application. I don't know, do you have something to add, Russell? Or
no, I think that's good coverage. Second question, how can you guarantee transparency of operation of technology with public review of match? How can you guarantee transparency of operation of a technology where the public review of match accuracy is not ethical or legal? I'm not sure what is meant by public review of match accuracy. But look, I think I can speak to some of the ethics in any event of using this technology. I think that ultimately these are technology. What importantly, one of the points that I think needs to be made is the use of these technologies. That we're not actually developing a lot that's new. That a lot of these technologies are actually out there and already being used. So it's the extent to which you can develop a piece of software that can be of immense public benefit, I think is incredibly important, and identifying where the public benefit with the aims of the research can actually outweigh and mitigate against potential harms. So it's, clearly it's very important to be cognizant of any harms that can come out of the development of such software. So for example, in creating training data sets to make sure that that data is collected in an ethical and legal manner, being aware of the legal, specifically the legal context in particular jurisdictions where this work is being done, and be mindful of how these tools are going to be, who has access to be able to use these tools, and how they're going to be deployed. So you need to be conscious of these things, absolutely. And it's creating these tools and bringing all this together and doing all of this training. These are some of the issues that we are facing right now, and I know that our colleagues are facing right now in terms of being able to do this and develop this infrastructure ethically and responsibly is of certainly of paramount concern. Did you want to add anything to that, Bryce?
No, I don't think that there's really much. I think that was just maybe it was talking about that, and then maybe also just matching it to child exploitation media. And so we are working with law enforcement in Australia to test a lot of this on child sexual abuse media. And we're also looking to work with Homeland Security's Victim Identification Unit. So we have connections in both of those realms. And so they're in the process of putting together databases to test this. And then a lot of our future work is trying to tailor it a lot more to that domain.
Great, wonderful.